Today will just be a summary of what exists, as well as some work that we've been doing on old data that hasn't actually been looked at before. And I mean, the point of today is so many in the audience here have so much more experience on the Bushveld Complex than I do. So if you see something that we've missed, please come speak to us afterwards. There needs to be more collaboration between geophysicists and geologists. And so the aim of today's talk is to, foster some of that collaboration. Just want to say thanks to the good group. I must admit the hardest person to work with is that little one over there. A great group of students. This is the research group in general, not just the seismic guys, but they create a good environment for doing research. So the takeaway from today's talk, what of that data is available? There is quite a bit. What does it tell us about the subsurface geology? And like I said already, look forward to this future talk by Janine Cole. So looking at regional, and then we're going to go into local. So seismic networks that cover the Bushveld Complex. Going back to the 1990s, Prof. Ray was involved in the global seismology study. And just to highlight something which then will zoom into the Bushveld Complex, they looked at Archean cratons, the Proterozoic mobile belts, and you can see here that the thickness of the Archean cratons were a lot thinner at around 35 kilometers, and the Proterozoic mobile belts were a lot thicker at about 45 kilometers, as well as in the Archean there was more felsic, lower crust, and in the Proterozoic was more mafic. But as soon as you then zoomed in on the Bushveld Complex, things looked a little bit different. And so this is teleseismic data that was collected during the South African seismic experiment in the 1990s. And you can see here's the edge of the craton over there. And on craton you've got a lot more blue colors, which correlates with about 35 kilometer crust. And off craton over here, the mobile belts, it's a lot thicker, like we said earlier, at about 45 kilometers. But as soon as you zoom in on the Bushveld Complex over here, it thickens. And so that was an interesting observation that came out of the study. Just to say, it wasn't just one study that found this. Several different studies that went back and looked at this data. You can see all 6 of these here, all in this region over here for the Bushveld Complex found thicker crust below the Bushveld Complex. Just in case there were any geophysicists in the audience, I'll put what methods were there because I wasn't going to remember all of that. Zooming into Eldridge's study that he did for his PhD, again, here's the Bushveld Complex, and there's thicker crust here, and also just found higher velocities in the lower and upper crust in this area, favor the continuous sheet model, which I'm not going to go into too much detail, and that'll be touched on in the gravity talk. But interestingly enough, and I'll put this here, maybe if people want to go back and look at it, just said that in the center there could be some disruption of the mafic layering due to thermal diaphorism. But just in general, the thing to be gleaned from these regional studies is that you've got thicker crust below the Bushveld Complex and a more mafic lower crust. And then moving forward, Africa Array came along and tried to expand on the network of SACE sites. And you can see down here in South Africa, several sites were put in and expanded into Namibia and Botswana. Okay. This is a more up-to-date image of all the stations that Africa Array has, including some of their temporary sites. And you can see tons of sites over South Africa. Northern Botswana, which I'll show you now, has been expanded. Northern Namibia, which is now being expanded into southern Namibia, and also these Botswana sites. And then in the Bushveld Complex themselves, I've got a map of the new sites that they put in here. So this is Namibia, the southern sites that have just been put in, and the Botswana sites. So 20 in Namibia and 20 in Botswana, and then 25 in the Bushveld Complex. I think I might have to say this to the desktop. I think it's having a heart attack. Try, it's not going forward. Try to notice yourself. Use an opportunity to get a drink if you didn't already. given these 20 stations to Africa Array to set up for 2 years in the Bushveld Complex to understand the crustal structure in this area and to infill some of the gaps from the 5 stations that they had during the SACE survey. These stations give data in real time, and so you can see this is a screenshot of what some of this data looks like. And this is actually an event, a seismic event that happened on the 7th of Feb this year. And so if you want to know more about this, you can speak to Ranta at the back of the room there. So that's on a broad scale, just to show what's available. So zooming in a bit more onto the complex itself, we're going to look at some of these seismic lines. So you can see I'll go into detail number 1, number 2, number 3, number 4, and the 5th one that we found. So I wanted to see how many students, I'm not going to play this video because I wanted to see how many geology students were in the audience. They're not, I think most of you know how seismics works. We're all okay about that. I'm going to skip over that. It's really just how the energy bounced off of the Earth. And so in order to get an image from seismics, you need a strong acoustic impedance. And so for gravity, you need something to have a density contrast. For magnetics, a strong magnetic susceptibility. But for seismic, it's acoustic impedance, which is your density times seismic velocity. And so in the Bushveld Complex and the surrounding rocks, there's several horizons that give a good acoustic impedance contrast. And this is just an example of one. So down here in the bottom right, you can see we've got the UG2, that in the first column is the sonic velocity log. Nothing really shows up, but in the density log, you can see down here, there's a peak. And when you multiply those two together, you get a peak on the reflection coefficient, which ultimately leads over here to a strong reflector that allows you to image the UG2. And so keep that in mind as we go through this talk. And so you're going to have instances like that for several other horizons that we'll be able to image on the seismics. So this is an image from Sue's thesis, and there were several regional seismic lines collected. Number 1 in the west here was a reconnaissance survey just to see what could be seen in the Bushveld Complex. Number 2 here in the western lobe, a south-north line over the Rooiberg group. And then in the middle here, we've got number 3. Number 4 goes over the northeastern limb, and then I'll show you now another line that goes in the south over here. So summary of these lines. 1 and 2 were connected by JCI, and they have 2 publications on them, but the data, as far as we know, has been lost. But I'll show you one of these lines now. And line 3 in the middle here was part of the South African National Geophysical Program, and has been looked at by 2 people. I didn't get a chance to ask Ray. I assume the data is still available if it has been published so recently, or may, but I'm uncertain if it's able to be reprocessed or it's just the existing migrated data. And then number 5 is this line on the eastern side here that goes across the southeast part of the Bushveld Complex. That was collected by Anglo, and that we do have the data for. I just wanted to draw your attention to this block up here. This is several seismic lines that are in this northwestern part of the Bushveld Complex up here, and those were also processed, were looked at in Sargent's 2001 thesis. So close, restart, close. Oh, okay, there we go. We should all have a beer.
Is it on the hard drive?
We put it on the desktop.
Yeah. Is that video embedded? Maybe just delete that slide.
though it looks very chaotic, all these purple and black lines are actually part of the seismic data that MUSAN has on the server upstairs. And so you can see over the Bushveld Complex, we have this number 3 line in the south, as well as this number 5 line going across there. So the Seismic Research Center is just a wonderful opportunity for students to learn from data that we've been able to get from industry. And so I think all of this was from AngloGold Ashanti. And so just to look at what some of these seismic lines look like, and you can see if they can form part of your research. The number 2 line in the west here was processed by Jeff Campbell, and thankfully he put a better image in his 2011 paper. It was quite difficult to see in the 1990 paper. But you can see here, it's the south-north line, and you've got these dipping layers. Just to highlight some of them here, we've got the base of the Pretoria group, and then throughout here you've got the layers of the Bushveld Complex, and at the top here is the base of the Nebo granites. And so you've got the lower zone and marginal zone pinching out to the south here, but then quite a thick succession of the main zone, upper zone in this region. But a structure in the center here. In terms of line 3, which is the southern line, this was processed by Terry Odgers for his thesis, and so you can see it moving from south to north. We go through the Transvaal supergroup, all the way through main zone, upper zone, into the granites, and then into the Karoo cover. And again, you can see these dipping layers down. The next slide will show some of the interpretation. Before I forget, in general, the side axis here is in two-way travel time. So you'll see values ranging from 0 to 4. You can approximately multiply that by 3 to get it into depths. So you can see here that at about 1, you would be at approximately 3 kilometers depth.
Is it exaggerated? Are the depths exaggerated, or is that real?
No, it's exaggerated.
So what are the real depths approximately?
I would have to check, but between 10 to 15. That's what I
Yeah, it's much more shallow.
And so this is some of his interpretation. And so again, we've just got these conformable layers of the Bushveld Complex, and right underneath it we've got the Transvaal sequence, but the marginal zone is being pinched out towards the south here, and you've got the granites on top. Fiona Sargent did her PhD also looking at this line, so not much more can be gleaned from it, but I just wanted to put it in there so everyone knows what's available. Looking at line 4 up in the top here, this was about the first time I started getting involved in the Bushveld Complex. We looked at this line about 2 years ago. Sue was looking at an ICD project drilling in this region. And so the line goes across here over the Malope Dome. It goes from the Rustenburg layered suite onto the granites. And so you can see zooming in on the 1 in 250 map here, you're going from Transvaal super rocks in the northeast, down over the Bushveld Complex, down onto the granites in the southwest here. It's looking like the laser photo. Seems to be, there we go.
It wants you to turn it off.
There's not much more I can say about this band than that. I think that's it. Yes. So Terry Odgers also again looked at this line. It was in a South African Geophysical Association conference publication. And so you can see the Transvaal sequence down here, and the Rustenburg layered suite on top, and the discontinuity here by the Malope Dome. This gives you a better idea of the dip here, Lou. So Fiona again looked at this line for her PhD. Apologies, I did flip the line so that it was the same orientation as the previous line. That's why, even though the font is small, you really cannot read any of those labels. And so look here, so Transvaal sediments again below this, the Bushveld Complex, and here's your Malope Dome, and is it the Parney Dome? And then the USGS came along and did a slight modification on her interpretation here and actually marked in the basement rocks here. Below, the blue is the Bushveld Complex, and then the brown is the Transvaal supergroup. So we, just to show you that the data is available, we do have it upstairs, and except unfortunately we only have the first part of the line and the middle part of the line, not the last part of the line. And this was just basic interpret that was done by correlating it with surface outcrop on where the boundaries between the different zones were. And like you can see here, there's some very strong reflectors in different sections, but in other regions it's quite difficult to pick up the exact boundaries. But you can pick up here at the base of the Transvaal. We do have a borehole in this region, so boreholes always make seismic easier, but unfortunately this borehole went down to 500 meters, and as you can see on the previous slide, that took us maybe to about here, so it really didn't help much. So we can only hope that Sue's ICDB project goes ahead, so then that will help. In terms of this line, so this is really what I started working on in the postdoc in the southeast here, but to warn you, I worked on it for about a week, a few years ago, and then Grant said, will you give a talk? And then I thought, oh, I need to put in this talk. Why don't I present on this? So this is what I did yesterday. So I haven't done as much as I can, but it's been a good impetus to get started on this again. And so this region down here is where this gravity high over here is, and the question about whether the extension of the Bushveld here into the Bethel lobe. And so the seismic line you can see goes over the granites here, and the green coming through here is part of the upper zone and main zone. It goes down over the granites, and then this brown here is this Waterberg, and down into the Transvaal. So it's quite an interesting line, lots to see. I think I definitely need a structural geologist, so if anybody's free next week, we can take a look at it. Also just to highlight the importance with geophysics of always combining your data set. And so this is the 1 in 250 geology on the left-hand side, but on the right here is the regional aeromag data. So this has a 1 kilometer line spacing, so you're going to miss out on a lot of the finer detail stuff, but you do get a picture of the regional. You can see here your strong signals in the northeast here is from the Bushveld Complex here and your magnetites. And down here, this strong signal here will zoom in, and there is actually some intrusive rocks here. But in general, a lot of the magnetic structures seem to correlate with these linear structures that have been mapped. So this is starting in the northeast. We're going over main zone rocks, Rushhook, Granophyre, and Nebo granites. And you can see here, Nebo granites, not too easy to see anything on the seismics, massive into the Granophyres. And you're starting to see some layering here on the upper zone, main zone, but then strong layering underneath. As we saw with a lot of the other seismic sections, the Bushveld Complex layering kind of continued on with the Transvaal layering below. So that's why I put a question of, is it Transvaal below, or is there also some of the Bushveld Complex up here? So I'll look in more detail just at some of the thicknesses that would be expected there. I didn't look in too much detail about that. In terms of this middle section here, it goes from the Nebo granite over this section of Transvaal sediments. And so you can see 1 through to 5 are the older to younger Transvaal sediments. And just to see what those look like on the seismic section, and we go back into the Nebo granites here. And it's definitely a complicated seismic section. So here's the Nebo granites on both sides, and this structure here seems to have something to do with this Transvaal block in the middle. It makes a bit more sense at the end. I'll stitch them all together, and it's a little bit easier to see, but I just wanted to take you step by step so you could understand each section. Over here we're going granites, Granophyre, back over the granite, and so on surface, or near surface, you're not seeing much because of these granites, but at depth you're starting to see this layering again, and this matches up with this Transvaal block that continues on the side here. D over here, again going over the granites, this Loskop formation, down into the Waterberg at Dwarka, and we start to see this very strong reflector coming through, close to surface, which would either be the Waterberg or the Peru supergroup. I'll look into more detail about that. I would assume you can't see much underneath because the strong reflector is taking away a lot of the energy, but yeah, you're going to see a lot below that. The strong reflector carries on here to the side, and this black arrow here is where this Waterberg group and this Gleicher group end, and so you would expect the strong reflector to come up to surface here, and so it definitely relates to this rock formation here. And then the strong layering of the Transvaal supergroup comes in, and here you can see you've got your Magaliesberg quartzites as well as diabases coming through, and so that seems to be this layering. And then the last section of this seismic profile, you can see here is the Transvaal, but then underneath it seems to be a bit more complicated. There's this Wits coming through in this region. Again, I'll look at thicknesses in more detail as I go forward. And you can see here on this geological map here that we're going through Transvaal sequence here, and then we hit the Eka that outcrops on surface. So we can't really see what's underneath it, but I'll show you now on the geological map how close by the Wits is. So is it Wits or not? So this is the end of the seismic line coming here, and then this is the closest Wits just to the southwest. So it is a possibility that these rocks are dipping underneath here. So I will keep you posted about that. So this is the line stitched together. So starting in the northeast here, we started over the Bushveld Complex. So these, we definitely have outcropping main zone, I think it was on surface or upper zone, sorry, and possible layering underneath here, the Transvaal and the rest of the complex. This complicated block in the middle that links to this these Transvaal rocks. And then again this layering that definitely seems to continue on either side of this block. This is this middle section here between this Transvaal layering and where we suddenly start to get this very strong reflector on the surface. So I would assume, but I'll investigate more, that maybe the energy is being absorbed here, that's why we're not seeing much underneath here, or is it a structural detail? And then wrong direction. The southern part of the line, the strong reflector keep coming through. The sediments that we see on surface, all the way to here, we see these Transvaal sediments, and then underneath these more complicated layers of sediments here. Is that what it is? Okay. So that's really what I added in yesterday, so apologies for that. You all have to help me solve the problem, you're now accomplices. So what this talk actually started as was stuff that I presented at Saga talk last year, Saga conference. And it was on a 3D seismic cube that we had over the Impala Platinum mine in the Western Bushveld Complex. And so the second part of the talk is about that. And so a big part of the talk as well was about integrating geophysical data sets. So not only do geologists not talk to, geophysicists not talk to geologists, but potential field geophysicists don't always speak to seismic geophysicists. So the aim of this as well was to get a bit more integration going on. To look at some features, looking at dikes, slumping or possibly potholes in this region, IRUPs, which stand for iron-rich ultramafic pegmatoids, so intrusives in this area. I'll show some pictures of those to explain them. Diapirs that we see in the Bushveld Complex, faulting, and then always with the aim of allowing for mine, well, better safety when planning mining. And so just to put you in context of the previous image I showed you, we're going to be looking in this area down here in the southwestern Bushveld Complex. So just south of the Pilanesberg, that's this big yellow circle. Okay, so this purple circle here was the yellow circle on the previous slide, and this black box here is our survey area, and you're going on top here from the Boer Granite Suite. This blue is the granophyres. This purple is the magnetite gabbro. This blue is the main zone into the brown of the critical zone, and then you're getting marginal zone and Transvaal here. And so all of the rocks are dipping towards the northeast. Stratigraphy-wise, even though the upper zone and main zone is what's outcropping on surface, the main point of the survey was to look down into the critical zone to look at the UG2 and the Merensky Reef, which is obviously the most economic. And yeah, some of the other chromatites, but mainly in this talk we're going to focus on the UG2 because it was easiest to map with the seismics. Just for those of you who aren't experienced in the Bushveld Complex, we get potholes. So this red here is the Morensky Reef. It's potholes that cuts down into the underlying reefs. And then in the middle here is this IRUP that I was speaking about previously, this iron-rich ultramafic pegmatoid. They're very often closely associated with one another. So this is kind of what you can expect to see on the seismics. This wasn't the first time people were seeing these on the seismics. They have been seen before. You can see these slight depressions in these strong horizons. So on these seismic images, you get depressions down here, and this is a plan view, these circular depressions. So this is what we were going to be looking for. In terms of IRUPs, what were we expecting to find? These are what the chromatite seams where they've been mining for the economic minerals, but these are the IRUPs that cut through. And so you either get them replacing the chromatite completely, or you get them just above the reef, or over here for number 3, they sometimes even go along the reef. What would these be expected to look like in seismic section? Here you can see this, on the side here, there's a strong reflector, and in the central region here it becomes quite rough. And that's due to, John Trickett said, due to the effect of IRUPs in the region. You can see this is a magnetic image here. They very often have strongly magnetized, either positive or negative, and so you can see these circles here due to IRUPs. Diapirs have also been shown to form in the Bushveld Complex, and so often due to disconformities in the basement or the heating of the complex resulted in this diapirism of this older transvaal rocks underneath, and this is what you'd expect to see. Again, have been seen for on seismics. In the top here, this is one of Jeff Campbell's image. This pink is the basement, and you can see it rising up. But some of these lower images here are a bit more high resolution, and you can actually see the layers rising up in these diapirs. Okay, so this is our region that we were looking at. And so this is the aeromagnetic data over it. And on the right-hand side, if you remember, there was that magnetite layer, and so that's why it's such a strong magnetic signal. And then through the middle here is a fault zone, which I'll show you has been mapped. For those in the audience who care, it was collected at a height of 40 meters with a line spacing of 50 meters. So a really high resolution if you consider the fact that the previous regional data I showed you was 1 kilometer line spacing. And so this is the basic interp before we got started. The magnetite gather is here. This mapped fault zone on surface, which also correlates with a series of dikes that are seen on the regional magnetic data. And then these highs over here, these pink ones, we assume are due to IRUPs. Something else you can see here, so if I jump back, you can see some dikes coming through on the magnetic data, and so we just try to process the data a bit to try better map the continuity of these dikes. So this is a vertical derivative of the data, and these black lines show the dikes that were mapped on surface, and this here just shows the ability that we could continue some of these dikes just using the process data, so you can better map the dikes. So that's the vertical derivative. We also looked at the tilt derivative, and all of these allow for better mapping of the dikes in this region. In terms of the seismic data, you can see here the strong reflector of the UG2 coming through. And so these are the parameters for the seismic data. The main thing to realize, to see here, is that the bin size was 7.5 meters, so it was a very high resolution survey. And as a result, we could see dips of up to 65 degrees. So able to see a lot of features here. You could resolve throws on faults of down to 10 meters at depths of around 2 kilometers. So this was the horizon that I mapped in, I think it was Kingdom Suite. And so you can see here, like I said, it's dipping towards the northeast. So the white is shallow depths, the blue is deeper down. And if we look at an interpretation of it, you can see this is where the fault zone comes through. That's why it's struggling to pick up the horizon in detail there. It's a bit difficult to see. There's a black outline here. And in general, this region here is shallower than you would have expected it to be. No, deeper than you would have expected it to be, sorry. So that's why I've marked it as a region of slumping, which we'll look in some detail. And then the question here is it's shallower in the southwest, which we would have expected, but you can see this height extends further than you would have expected. So is this a region of diaparism? It's piqued our interest, and then we went to look in this region. In terms of the slumping, I originally went looking for potholes, but this region seems to be a huge slump structure. So it's about, I think it was about 5 kilometers in length and about 2.5 kilometers in width. And so I took out some of these profiles and then the profiles at right angles just to better understand these structures. So relative to the map I've shown you already, we're in this central region here. And you can see all these magnetic highs we would assume due to IRAPs. And so looking at this number 2 profiles here, I'll show you what it looks like. Okay, so just to get your eye in, the strong reflector here is the UG2, and you can see how it slumps down over here in this region. And it's slumping down by about 0.1 seconds, so approximately about 400 meters down from where you would have expected it to be. I've just briefly shown some faulting there. You also get over here a rough reflector. It could be one of these IRAPs. Is this a smaller pothole here or smaller slump structure? And you can see there's also the overlying layers seem to have been disturbed. So this is the inline. We're now going to look at the cross line at 90 degrees to it. And so it's not as pronounced because now this is going down dip, so that's why. But you can see here's the UG2, a region of rough reflectivity, possibly an IRAP over here, and then the UG2 continuing down here. So quite faulted in this region. So we've gone with saying it's a slump structure rather than a pothole just because it is such a large region. But delving deeper into it, everybody seems to have different ideas of how big a big pothole can be. So it's open to interpretation, but we decided to hedge our bets by saying slump structure. In terms of the diapir, so this is the aeromagnetic data I showed you previously. We're going to be looking at this region over here, mainly in this, the southern region. So this is the profile I'm going to show you on the seismic section. This is that fault zone or dike structure cutting through. These red arrows are just here for reference when we look at the seismic section. And this black dot here is a borehole. Okay, so this is the seismic section. Again, these red arrows mark either side of the fault zone. So this is this fault zone dike region. And here's the borehole, which actually does intersect an IRAP or replacement pegmatoid. But you can see deeper down here, this upderming of the sediments, which we've marked as a dike here. And I'll try to insert some of the faults in this region. But yeah, a very complicated region, and there is the pushing up of the UG2. The UG2 is not as impacted as these deeper down sediments, but there is this upturning. In terms of this fault zone and this gabbro, the magnetite gabbro towards the east, so we're focusing on the eastern side of the map now, I just pulled out a profile, a northwest-southeast profile that intersects this black borehole over here and cuts across this fault zone dike region, just to see what some of the structures look like. And you can see here is your UG2 coming through, and it's disrupted in the middle here, and this red line, this red arrow, shows exactly where the fault zone is. So you would expect it to be disrupted, but it's just interesting how the sediment at the bottom seem to be flowing or deformed in this region. There is definitely an IRAP over here that's intersected by the borehole, but I would expect if the IRAP continued all the way down to be quite diffuse reflectivity, whereas here you can see quite good reflections on the layers that seem to be going upwards. If anybody knows what this is, let me know. Just in terms of IRAPs, what do they look like on the seismic sections? So here's this the magnetic data I've been showing you. So we're focusing on the central area here. You can see this dike coming through here, strongly negatively magnetized. So the red triangles are wells that intersected IRAPs, whereas the black circles are wells that didn't intersect IRAPs. And so what I tried to do was take out seismic profiles that went over these wells that intersected IRAPs, just to better understand what this model would look like on the seismic sections. And so looking at this first example of where the IRAPs come and replace the reef completely, which is what you would kind of expect to see, is here you've got your strong UG2 reflector, and then in the middle here, you don't see anything because it's completely replaced it. And we know there's an IRAP here because here's the borehole, and it says it's intersected the IRAP up here, and so I'm assuming it's going all the way down here and it's completely replaced this horizon. This is the line at 90 degrees to it, and again you're seeing the strong reflector, this region of no reflectivity, and then going down here again to strong reflector. Again, you're using up reflectivity here. So I've put it down as an example of number one. In terms of when it's above the reef, and here you can see you've got a strong reflector, and then it becomes rough reflectivity. So you're not losing the reef completely, but it seems that the IRAP here that this borehole has intercepted is affecting the seismic energy from getting down to the reef and imaging the reef. And then it continues smoothly here. Again, this is the line at 90 degrees, and you're not getting as broad a region of reflectivity, but it's intersecting the IRAP over here. So I've said this is an example of the number 2 IRAP. Parallel to the reef, so a bit busy here, but you can see here is the UG2, and then here's a borehole that's come out and a deviated borehole here, and I've tried to zoom into this area over here. That's what this box is. And you can see in the borehole it says IRAP over here, and then below that it says UG2, which you cannot see very easily. And so it's still intersecting the reef and an IRAP above it, and so it seems you've got this IRAP going along the reef here and adding to the reflectivity that we're imaging. And again, the line at 90 degrees, and you've got the IRAP here and then the reef underneath it. So it seems to be going along the reef. In the last example, you've got the UG2 on either side, this rough reflectivity region, so I would have thought it's been completely replaced, but if you look at the zoom in borehole image, you're still seeing the Moraine here and some of the UG2, but there's an IRAP as well. So possibly the IRAP is actually remobilizing the reef in this region. And similarly in this image here at 90 degrees. But UG2, but over here you're still seeing IRAP and you're still seeing the reef. Lastly, the thing that we see is dikes. So you never see dikes on seismic section, and you're not actually seeing the dike here, it's more the discontinuity that has been caused. So here's the UG2 coming through, and here's this bump in the horizon, and this red arrow correlates with this red arrow here, and this red line is where the seismic section is. So you are seeing the dike on the seismic section, but it's because of the offset that it's causing in the horizon. So a wealth of data a wealth of information that we can glean from this high resolution seismic data. And so well, you can see that over 50% of the reef in this region is disrupted by dikes, slumping structure, IRAPs. I did it again. First time I gave this talk, Ray was like, "You've got babies on the brain." This obviously wasn't the change or faulting. Obviously still have it on the brain. In terms of dikes and how it impacts mine safety and planning, the dikes replace the reef completely, so you can't do much about it there. Safety-wise, you'll have to take it into account. The slumping, like I said here, this was, it actually should be bigger, so 5 kilometers compared to, most people I seem to say liked 1 to 500 meter widths for potholes, although some people have said it's large, much larger in the northwest of the Bushveld. So, slumping structure pothole is very disruptive in this region. But you could still possibly recover the reef in this region if you had extra safety measures. The diagram, which I spelled correctly, it actually brings the UG2 to slightly shallower levels than you would have would be expected. So it was about 175 meters shallower than where it would have been. So this would reduce mining costs, but you need additional safety measures because of the faulting. The fault zone, I was quite surprised it wasn't more disrupted. I forgot to point it out in more detail, but obviously you would require additional safety measures here. And then IRAPs replace the reef, but it was interesting to see that in some instances where it's parallel to the reef or remobilized as you possibly could still recover the reef in this region. So that was the end of the talk for Saga, and the only thing to say on this is to watch out for another Saga talk by Level, who's busy working on some of the other potholes in the Western Bushveld Complex. So this is a seismic attribute of the horizon that she's created and some of the potholes that she's been identifying. So she should be finishing at the end of this, but she will be finishing by the end of this year. So she'll come give us a geotalk when she's done. And that's the end of it. So just a huge thank you to the sponsors. I think that's what made the Seismic Research Centre possible. Data. We have tons and tons of data, so it's exciting for student projects, sponsorship, as other sponsorship as well, trust sponsorship, and also software. Software costs a lot, so without the software that we sponsored, I don't think we'd be able to do all the work that we do.